Does this formula look familiar? Well, it should. This is the formula for taking the derivative of a product of two functions. It's quite a simple formula, and it looks quite nice. But is there something similar to this for the antiderivative? Well, the short answer is yes, but not quite as nice looking or as easy to execute. Now, I'm not going to explain how to derive the formula, but I am going to explain how to use it. And without wasting any more of your time, just here's the formula. You may be familiar with the term u, classically used as a substitution variable, and you'd be correct in thinking that. However, we don't just have a single substitution, but in fact we have two different substitutions. Our other substitution is not v, however. It is instead dv, since it will incorporate the dx or the dt or any other variable that you have. Alright, because it is quite difficult to explain what our u and dv substitutions should be, we'll just jump straight into an example. The antiderivative of x times e to the x dx. We know how to take the antiderivative of e to the x, but we cannot just initiate a u substitution because we'd end up changing our variables from x to u. This is really only solvable by integration by parts with all of the tools that you should currently have. We'll start by determining a u substitution. Typically we want our u substitution to be an algebraic expression or polynomial, because we'll be differentiating u, and having it reduce closer to 0 is ideal and makes things a lot easier. You'll see what I mean in a second. Because x approaches 0 when we differentiate it, we will make that our u. Like any other u substitution, we would then take the derivative of u to get du, which is just equal to dx. Next is our dv substitution, which is just made up of everything we have left. It is important that you choose a dv such that integrating it is not impossible, but since e to the x is the only thing remaining, and it is quite easy to integrate, so our dv will just be e to the x dx. To get v, we integrate e to the x, which is just e to the x again. Great, we have our substitutions. We can now simply plug this in, just like we would for the product rule for derivatives. Our u and v multiply together to get the first part of the formula, which is x times e to the x. And then we subtract that by the antiderivative of v du, which is e to the x dx. We only have one more step, which is to solve for the antiderivative of e to the x. That's just e to the x again, so our answer is x times e to the x minus e to the x plus c. Or you can write it as e to the x times the group of x minus 1 plus c, but that's not entirely necessary. Never forget the c. That's one of the bases of our antiderivatives. Gotta add that integration constant. Here's another example. The antiderivative of x squared e to the x dx. If you'd like to pause the video and give it a try, go ahead, but I will warn you that you may have to perform integration by parts multiple times. Alright, so we can see that e to the x goes down to 0 when differentiated, and e to the x is easily integrable, so we can choose u to be x squared and dv to be e to the x dx. That makes du 2x dx and v e to the x. Multiply u and v together to get x squared e to the x, and subtract that by v du, which is 2 times the antiderivative of x e to the x dx. Uh-oh, we can't integrate the new antiderivative normally. To solve this, we have to perform integration by parts again. To save the headache, we've already solved the antiderivative of x e to the x dx, which we did in the last problem, so we'll rewrite the complete answer as x squared e to the x minus 2x e to the x plus 2 e to the x plus c. Alright, Up next, feast your eyes on this. The antiderivative of the natural log of x dx. It may at first glance look like this is impossible to figure out without traditional methods, but it really is far simpler than you may think. We only have one function here, but we still have a product of functions in this scenario because we can multiply ln x by 1. Sweet! We now have our u, right? 1 goes to 0 when we differentiate it, so that must be u. And dv must be ln x, so wait. To get v, we have to integrate ln x again, and that doesn't work since that brings us back to our original problem. What do we do now? Well, if one substitution doesn't work, try changing your substitutions. Let's have u be ln x and dv be 1 dx. That makes du equal to 1 over x dx, or x to the negative 1 power, and v equal to x. Now we can multiply u and v to get x ln x, and subtract that by the antiderivative of v du, which is 1 dx. That just means our answer is x ln x minus x plus c. Or if you really wanted to factor it, x times the group of ln x minus 1 plus c. If you'd like to practice, feel free to take a look at the following practice exercises. The solutions will come roughly 5 seconds after each problem, so pause the video if you'd like to try each for yourself. Most of the problems don't have a step-by-step solution, but there's always calculators on the internet for that if you really need it. These are more just guiding questions. The answers to the antiderivatives are given, but some of them may be a little bit more challenging than the others, and you might have to be a little bit creative. This is only a basic introduction to integration by parts, and I really do mean basic. There are more integration by parts methods and far greater applications, but this is just a very, very reduced and simplified explanation. Thank you for supporting me by watching this video.